Okay, this is chapter 4.6, the fundamental theorem of algebra. Essential question is, how can you determine whether a polynomial equation has imaginary solutions? What you will learn: use the fundamental theorem of algebra, find conjugate pairs of complex zeros of polynomial functions, and use Descartes' rule of signs. So lots of exciting stuff here, so let's get going. Okay, the fundamental theorem of algebra. The table shows several polynomial equations and their solutions, including repeated solutions. Notice that for the last equation, the cubic, the repeated solution is x equals -1. It's counted twice. Okay, so equation 2x minus 1 equals 0 is a line with a slope of 2 and a y-intercept of -1. It is of degree 1. Its solution is 1/2 because that's what makes that equation 0. Subtract 1, divide by 2, and you got it. Number of solutions, 1. X squared minus 2 equals 0 is a quadratic. It would be a parabola. It would be shifted, or I'm not shifted. It would be y-intercept of -2. So it is shifted. Degree 2. And it's got two solutions, positive and a negative square root of 2. Because you add 2 and take the square root, you get plus or minus square root 2. X cubed, so x cubed minus 8 is a cubic, y-intercept of 8, degree 3, and it has three solutions. One that is real, 2 that are imaginary complex, totaling 3. So this thing crosses the x-axis in one place at 2, and then it has 2 imaginary solutions. And then finally, the last one, x cubed plus x squared minus x minus 1 equals 0, has a degree of 3. It has 3 solutions, -1, -1, and 1. And that is what they were talking about up above with the repeated solution, x equals -1, counted twice. So this has a multiplicity of 2. So in the table, note the relationship between the degree of the polynomial and the number of solutions. So degree 1, solutions 1, degree 2, solutions 2, degree 3, 3, degree 3, 3. This relationship is generalized by the fundamental theorem of algebra, first proven by German mathematician Carl Friedrich Gauss, 1777 to 1855. Okay, so that is the fundamental theorem of algebra. The degree of a polynomial is equivalent to the number of solutions. So the core concept says, the fundamental theorem of algebra, theorem, if f of x is a polynomial degree n, where n is positive, then the equation f of x equals 0 has at least one solution in the set of complex numbers. Corollary, if f of x is a polynomial degree n where n is positive, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions. Each solution repeated 3 times is counted as 3 solutions, and so on. Okay, so as long as you're counting those repeated solutions as individual solutions, then this theorem holds. Okay, this is example 1, finding the number of solutions or zeros. How many solutions? So let me get my highlighter. And it says, how many solutions does the equation x cubed plus 3x squared plus 16x plus 48 equals 0 have? The first thing you want to do is verify that this is in standard form and make sure that your largest term is first. You want to know what the largest degree, the degree of the polynomial is the power of the first term when it's in standard form. So since that is 3, this has 3 solutions. And the next one, how many zeros does the function f of x equals x to the 4th plus 6x cubed plus 12x squared plus 8x have? 4, 3, 2, 1. This is in standard form. First term is x to the 4th. Therefore, it has 4 solutions by the fundamental theorem of algebra. All right. Now, it doesn't say here what the solutions, to find the solutions, but it does say finding the number of solutions. But if you were to find the solutions like the book shows, what you would do is you would take this first one here, that is a cubic, and remember that you take P over Q, all the factors of P divided by Q. P is your constant, and Q is your leading coefficient. So I want all factors of 48. So if I were to do this, I'd do 48 is 1 times 48, or negative 1 times negative 48. Okay, and I'm not going to show all the negatives because it just fudges it up and makes it busy looking. So I'm just going to skip the negatives and just say plus or minus at the end. So 2 times 24, 3 times 16, 4 times 12, 5 won't go, 6 times 8. So these are all the factors of 48. So my possible solutions are that P over Q, which in Q is 1, so that makes it easier. So we get 1, 2, 3, 4, 6, 8, 12, 16, 24, or 48. So the book shows the answers, and it's plus or minus, by the way. So I would have to try 1 or negative 1, 2, negative 2, 3, negative 3, and I'll do 3 first. So to find the solutions to a cubic, you do synthetic division. So this is a degree, or you take the coefficients, 1, 3, 16, 48, and you put them here, making sure none got skipped. 3, 2, 1, 0. So it's 1, 3, 16, 48. You bring down your first term and multiply and put the product here and add. 3 times 9 is 27. 27 plus 16 is 43. And 3 times 43 is definitely not negative 48. So obviously it didn't work. Okay. In other words, 129, 9 and 8 is 17, 6, 7, 177. If that is not 0, this is not a factor or a solution. All right. So I'm going to back up. I'm going to put a negative sign here and bring down your 1. Negative 3 times 1 is negative 3. 3 plus a negative 3 is 0. Negative 3 times 0 is 0. Bring down the 16. Negative 3 times 16 is negative 48. And I got a 0 here. And I like to put a box there to show that that's the remainder. So if negative 3 is a solution, then x plus 3 is a factor. And then this is the polynomial left over after constant, linear, cubic. Squared. So that's 1x squared plus 0x plus 16. So those are the two factors there. And then, so if x plus 3 equals 0, then x equals negative 3. If x squared equals 16, or x squared plus 16 equals 0, and I subtract 16 to the other side, I get x squared equals negative 16. Take the square root of both sides, and I get x equals plus or minus, and the square root of 16 is 4, and since it's negative, you have an I. So it's plus or minus 4i. So there are my 3 solutions: negative 3, 4i, and negative 4i. Okay, I'm not going to do this one here, but that's how you would do it. You'd first factor out an x, get this down to a cubic, and then do the same process. So this only asked us how many solutions there are, and it's 3 and 4. So after this example, you should be able to do problem numbers 3, 4, and 6. Okay, example 2, finding the zeros of a polynomial function. Find all the zeros of f of x, and it's a 5, 3, 2, 1, 0. It's in standard form. So I'm going to highlight the first term right there. The degree of the polynomial is 5. So there are 5 solutions. We are looking for 5 solutions. This time it does say find all the zeros or solutions. Okay, so it has 5 zeros. They might be duplicates. They might be repeated. So, and now what we do is we take factors of the constant divided by factors of the leading coefficient, and luckily that's a 1. So we're just going to do factors of negative 8. So factors of negative 8 are 1 times 8, and if the 1 is negative, or 1 times negative 8, the 8 is negative. And then, so I'm just going to show all of these because there aren't many. 2 times negative 2 times 4 and 2 times negative 4. And that's it. We're done. Divided by 1 would give us plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. So we do have 8 possible outcomes for solutions, but 5 of these are solutions, 3 aren't. So it shouldn't be too difficult to find the ones that are. So I'm just going to start with 1, and I'm going to do it as if I don't know the solutions. So I'm going to put a 1 here, and then I write my synthetic division. Now remember, there is no x to the 4th. So I think of that as 0x to the 4th. I can't forget that in my synthetic division lineup. 5, 4, 3, 2, 1, 0. So 1x to the 5th, 0x to the 4th, 1x cubed, negative 2x, negative 12, or negative 2x squared, negative 12x minus 8. So it's 5, 4, 3, 2, 1, constant. Bring down your first term. 1 times 1, put the product there and add. 1 times 1, put the product there and add. 1 times 2, add them. 0, negative 12 times 1 is negative 12, and I get negative 20. Okay, this is not 0, so 1 is positive, 1 is not a solution. So I'm going to do that. Okay, so I'm going to try negative 1. Okay, and rewrite it all. 1, 0, 1, negative 2, negative 12, negative 8. Bring down your first term. Negative 1 times 1, negative 1. Add it to 0, negative 1. Negative times a negative is positive. 1 times 1 is 1. Add, get 2. Negative 1 times 2 is negative 2. Add them, get negative 4. Negative 1 times negative 4 is positive 4. Negative 12 plus 4 is negative 8. Negative 1 times a negative 8 is 8, and that gave me a 0. So negative 1 is a solution. That means x plus 1 is a factor. Okay, so then I'm left with this. So now I can think of this as x plus 1 times what was left over here. So constant, linear, square, cubic, quartic, x to the 4th minus x cubed plus 2x squared minus 4x minus 8. Okay, and so now we're going to, this times this equals this. All right, so now I've got to do this again. So this time I'm going to try another 0. I already know it's x plus 1. Now I got to find what other one it is. Let me change colors now so we're on to a new one. So now I'm going to choose one of these here, and I'm going to start with this in my synthetic division. So I'm going to have a 1, negative 1, 2, negative 4, negative 8, and now I'm going to try 2. Let's see. Yeah, let's try 2. Bring down the 1. 2 times 1 is 2. Negative 1 plus 2 is 1. 2 times 1 is 2. And okay, so then 2 plus 2 is 4. 4 times 2 is 8. Negative 4 plus 8 is 4. 2 times 4 is 8. Negative 8 plus 8 is 0. Woohoo! Now I know that x minus 2 is a factor. So now I'm just going to list these now. So now I have x plus 1, x minus 2, and now this is my polynomial: constant, linear, square, cubic, x cubed plus x squared plus 4x plus 4. Okay, we're breaking it down. We're finding all of the roots. So now I have this here, and I still can't figure out just by looking at it what would this factor out to be. So I'm going to continue here. So it's -1 so far. 2 is a possible answer, +2. Let's try -2. So now let me switch colors, and I'm going to do -2 times, and this is 1, 1, 4, 4. So I'm just going to bring it from here. 1, 1, 4, 4. Bring down the first term, -2. 1 plus -2, -1. That would be 2. 4 plus 2 is 6. -12, -8. Not 0, not a solution. So I'm going to erase that. -2 is not a solution, but +2 is. Okay. Let me get rid of this circle. All right. So 1 is -1 is, +2 is. Now I'm going to try 4. So I'm going to rewrite this again. 4, 1, 1, 4, 4. Bring down the first term. 4 times 1 is 4. 4 times 4 is 16, 17. This is all positive. So this is just going to keep getting bigger. So I don't want to waste my time. So I'm going to stop with that. And I'm going to not use 4. I'm going to use -4. -4 will make this thing oscillate between positive and negative. So it's 1, 1, 4, 4. That gives us a better chance of hitting 0. Bring down a 1. -4 times 1 is -4. 1 plus a -4 is -3. Negative times a negative is positive. 4 times 3 is 12. 4 times 12 is 48 times a -4. This is getting really big. It doesn't work. Okay. All right, so as I go larger with these numbers, they're not going to work because these numbers are going to start getting bigger. So I'm done with checking these. I need to now look at this and say, okay, what can I get factored out of this? Okay, so now what I want to focus on is I know that the 5 solutions are right here out of these possible 8, because every constant over the leading term is a possible solution. So I have not checked to see if -1 works more than once or if -2 works more than once. Remember, we can have multiple roots or solutions repeated. So I'm going to try -1 with these numbers here now. So I'll do it in blue. So now I'm going to try -1 again and see if -1 works twice. And I'm going to use this 1, 1, 4, 4 here because that's this function here. 1, 1, 4, 4. Bring down the first term. -1 times 1 is -1. I get 0. -1 times 0 is 0. Bring down the 4. -1 times 4 is 4, or -4. And I do, in fact, get a 0. So that confirms that I now have these two, x plus 1, x minus 2, and now another x plus 1. Because this -1 worked, and now it's going to be constant, linear, quadratic, so it's x squared plus 0x, which I won't write, plus 4. Okay, and now that I have that, now I know I have imaginary solutions. So my solutions are going to be x equals -1, x equals 2, x equals -1, and then I'm going to take x squared plus 4, set it equal to 0, subtract 4, and solve for x. So x squared equals -4. Take the square root of both sides, and I get x equals plus or minus 2i, because the square root of 4 is 2, and the square root of -1 is I. All right, so I could have said it was x plus 2i, x minus 2i for the factors. So there are my solutions. I had a -1 twice. I had 2 once, and then these two imaginary. So 2 plus 1 is 3, plus these two here totals 5. All right, so those are the 5 zeros for that quadratic. At this point, you should be able to do problems numbers 10, or 9, 10, and 12 on your exercises. Okay, so a new term called complex conjugate. Okay, so pairs of complex numbers in the form of a plus bi and a minus bi, where b is not 0, because then the imaginary unit would go away and it'd be a real number, a. They're called complex conjugates. In example 2, notice that the zeros, 2i and negative 2i, are complex conjugates. So 2i, so we got a solution of -1, 2, -1, 2i, and -2i. Okay, they're conjugates of each other when the sign's different in between the a and the bi. In our case, in the last problem, a was 0. So it's 0 plus 2i and 0 minus 2i, if you will. Okay, so the next theorem states the complex conjugate theorem. If f is a polynomial function with real coefficients and a plus bi is an imaginary 0 of f, then a minus bi is also a 0 of f. So just like the last problem we did, 2i was a 0, -2i was also a 0. If I had a conjugate, if I had a solution that was, say, 4 plus 7i, then I can conclude from the complex conjugate theorem that 4 minus 7i is also an imaginary 0. Okay, and that's the complex conjugate theorem. Okay, so example 3 is using zeros to write a polynomial function. And so it says to write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1. Okay, so the coefficients have to be rational, no irrational coefficients, no square root of 3x squared, that kind of thing. And the zeros are going to be 2 and 3i. Okay, keep in mind the complex conjugates theorem. And so if we have a leading coefficient of 1, then I know it's something x. So let's call it f of x. And it equals 1x to some power. Now there's a 0. So x equals 2. This means x equals 2. And this means x equals 3 plus I. Okay, those are zeros. Since 3 plus I is a 0, the complex conjugate theorem states that x equals 3 minus I is also a 0. So there is x equals 2, x equals 3 plus I, x equals 3 minus I. That is 3 solutions. So now I know that I have a cubic. So polynomial function of least degree. So we're going to have at least 3 solutions, or only going to have 3 solutions. Therefore, the leading term is x cubed. So in order to solve this, you want to get all of these equal to 0. So you take all of your factors, set them equal to x. So you say x equals 2, x equals 3 plus I. Complex conjugate theorem tells me x equals 3 minus I. And now I want to get 0 on one side. So I'm going to subtract 2. And that is going to give me the factor x minus 2 equals 0. I'm going to subtract 3, and I'm going to subtract I from both sides. And when I do that, I get x minus 3 minus I equals 0. And then when I subtract -3 and I add I to cancel these out, then I'm going to get x minus 3 plus I equals 0. Okay, so there are our 3 factors, x minus 2, x minus 3 minus I, and x minus 3 plus I. So now I'm going to write f of x equals x minus 2, x minus 3 minus I, x minus 3 plus I. Okay, and what I'm going to do now is I'm going to rearrange my parentheses. So this is the same as saying f of x equals x minus 2. And if I pull this x out and I put it outside the parentheses, like let's use a bracket, x minus, this is going to be 3 plus I when I distribute. Make that a neater parenthesis. Okay, so if I take a -1 out here, -1 times 3 is -3, -1 times I is -I. So I have x minus the quantity 3 plus I. And then I will also do this again and put x outside minus 3 minus I. Okay. Whew. All right, so once I've done that, I can rearrange my parentheses. So then I take f of x equals x minus 2 is patiently waiting. I'm going to move these parentheses because once we subtract and add, order of operations say work left to right, but order doesn't matter. It's commutative. Now I can say this is going to be x minus 3 plus I in parentheses is the x minus 3 now. So all I'm doing is moving the parentheses. That's the associative property. And I'm going to do it again. And I'm going to put the parentheses around x minus 3. And I'm going to put minus I outside. So what does that mean? Well, I have an x minus 3 twice. So now I can rewrite this as f of x equals x minus 2 times x minus 3 squared minus I squared. Because this is multiplication, I times a negative I is negative I squared. Okay, so this is starting to pan out. It may not seem like it yet, but once I do this, now watch what's going to happen. I'm still going to have the x minus 2. I'm still going to have the x minus 3 squared, but minus I squared. I squared is -1. Minus a -1 is +1. Okay. And then I'm going to FOIL, if you will, inside here. That's going to be x minus 2, stays there, patiently waiting. X minus 3 squared, remember, if that means x minus 3 times itself. And that's going to give us x times x, which is x squared, minus 3x, minus 3x, minus 6x, and then a negative times a negative is positive. 3 times 3 is 9. I'm doing FOIL very quickly now. You should be able to do that. X squared minus 6x plus 9 plus 1. Sitting there going along for the ride. Okay, and now it is getting more simplified. And we're going to end up with x minus 2 times x squared minus 6x plus 9 plus 1 can be added and say plus 10. All right. So now that we've done that, I'm being more detailed in the book. I can then distribute these. So it's going to be f of x equals, and I'm going to color code this now because it's getting messy. X times x squared is x cubed. X times -6x is -6x squared. X times 10 is plus 10x. And now I distribute the 2. -2 times x is -2x squared. I'm going to do this vertically. -2 times a -6 is positive 12x. And a -2 times a positive 10 is -20. All right, so I'm going to then just simplify this, and I get f of x equals x cubed minus 8x squared plus 22x minus 20. Whew. And there's our polynomial. Leading coefficient of 1 with the least degree, which is 3. So the answer to this problem is f of x equals x cubed minus 8x squared plus 22x minus 20. Okay, so after doing that, you should be able to do problem numbers 21, 22, and 24. Okay, Descartes' rule of signs. French mathematician René Descartes, who lived from 1596 to 1650, died at the ripe old age of what, 54, 55, somewhere around there. Well, he found the following relationship between the coefficients of a polynomial function and the number of positive and negative zeros of the function. So his Descartes rule of signs says that if f of x is a polynomial, where a sub n x to the n plus a sub n minus 1 x to the n minus 1, and again, what that means is if our first term was 5x to the fifth, then it's going to be the fourth term times x to the 5 minus 1, which is 4, all the way down to a constant a sub 0. That's all that means. Okay, so any polynomial with real coefficients, the number of positive real zeros of f is equal to the number of changes in signs of the coefficients of f of x, or is less than this by an even number. What? The number of negative real zeros of f is equal to the number of changes in the sign of the coefficients f of negative x, or is less than this by an even number. Okay, so we're going to explain that a little more deeply in example 4. Okay, so here we go. Using Descartes' rule of signs, determine the possible numbers of positive real zeros, negative real zeros, and imaginary zeros for this function. Okay, so the first thing I'm going to do is we'll look at f of x, and this is positive. That's not a very good plus, it looks like a T. This is, let me change to red. This is positive, this is negative, this is positive, this is negative, 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 negative. So what you want to do is say, okay, there's one sign change, there's two sign changes, there's three sign changes, and the sign never changes again. So I got a total of 3 sign changes. That tells me there are, and if you go back here, the number of positive real zeros equals the number of changes in the signs of the coefficients. So there are possibly 3 real zeros or an even number less. So you could say, or 1 real zero. That's what that means. Okay. So here it says, or less than this by an even number. So once you get a value, you divide, subtract 2, subtract 2, subtract 2 until you get down to 0. So this has 3 real zeros or 1 real zero by Descartes' sign change. Now we're going to do f of negative x, which is negative x to the 6th minus 2 times negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x to the 3rd minus 6 times negative x squared minus 8 times negative x minus 8. So I need to do f of negative x and change all the signs. So a negative x to an even power is x to the 6 positive. Okay, and this is a negative times a negative, so it's positive 2x to the 5th. And this is a positive times a negative, so that's negative 3x to the 4th. Negative times a negative is positive 10x cubed. Negative times a negative is positive 6x squared. Negative times a negative is positive 8x minus 8. Okay, so we have oh, I'm sorry, mistake right there. Negative x to the 4th would be positive, so this is positive. So it's negative x times negative x times negative x times negative x is positive x to the 4th times 3, which is 3x to the 4th. Cubes keep the sign negative, evens make the sign, so here's another problem. Negative x squared is positive x times a negative 6 is a negative 6x squared. So my mistake there. Be careful of your signs. I wasn't, and I would have gotten the wrong answer. And so there we go. So now we have a positive, a positive, a positive, no sign change until here. And it became negative, then it went back to positive, and then it went back to negative. That tells me that there are 3, and then over here, if we go back, the number of negative real zeros is equal to the number of changes of sign of the coefficient, or less than by an even number. So there are 3 real negative zeros or 1 real negative 0. So what that means is if I had a coordinate plane, whoa, that was good. Let me do it the right way. If I had a coordinate plane, what this means is this is a 6-degree polynomial. It's going to look like this. 1, 2, 3, 4, 5, 6. Okay. And it's opening up because it's positive. So my end behavior is going to positive infinity both when x goes to positive infinity and negative infinity. So I can have as many as 3 zeros that are negative. So it could be over here or 1. But I can have 3 real zeros that are positive or 1. Okay, so I've got to figure out where this is going to end up. All right, and that's the kind of the idea of what Descartes' rule explains. So let me get these out of the way. So once we do that, let me bring a table in. Oops. Mess that up a little bit. Okay, so here's a table. We can have positive real zeros, we can have negative real zeros, we can have imaginary zeros, and we can have a total of zeros. Well, looking at the first term, 6, 5, 4, 3, 2, 1, 0. This is in standard form, and the first term, power, degree, when it's in standard form, tells us how many total zeros there are. So my total always has to be 6. Okay, so our total is always going to come out to be 6 because that's the degree of the polynomial. So this told us that there's a possibility of 3 real zeros. So that can be 3. And if that is 3, then the number of negative real zeros can be 3. And 3 plus 3 is 6. So if that happened, there can't be any imaginary. There also could be 3 real zeros, 1 negative real zero, because it's either 3 or 1 by the Descartes rule. And if that is the case, then there'd be 3 real, 1 negative, and I need 6, so 2 have to be imaginary. Then I could get 1 positive real zero, and in that case, I could have 3 negative real zeros totaling 4. So that means there's an imaginary of 2 to total my 6. Or I could have 1 and 1, and that's only 2, and I need 6, so that's 4 imaginary zeros. So those are the total possible locations of our zeros in the polynomial degree 6. Okay, so there's example 4. Now you should be able to do problems 33, 34, and 36. Okay, so real life application that involves large values like this and small values like this are going to require a calculator to be accurate. So anyhow, example 5, real life application. A tachometer measures the speed in revolutions per minute, or RPMs, at which an engine shaft rotates. For a certain boat, the speed x in hundreds of RPMs of the engine shaft and the speed s in miles per hour of the boat are modeled by the function s of x equals this polynomial function. Okay. Okay, so the first thing you should do is focus on whether the polynomial is in standard form or not. 3, 2, 1, 0. It is. It's degree 3, and it's got a positive leading coefficient. So that right there tells me that it can look like this. End behavior and up, down, up. And it could also do this as well. There may not be a relative maximum or minimum. It might go up, flatten out, and go up again. So these are our 2 possible graph scenarios with a positive x cubed for our first term. The next thing we want to do is focus on Descartes' rule. So if I take this and, oh, by the way, it says, what is the tachometer reading when the boat travels 15 miles per hour? Well, that's our speed in miles per hour, so that's our s of x. So the first thing we do is substitute in 15 for that, and get 0.00547. Oops, pen went wacky on me there. Let's try that again. 5, 4, 7 x cubed minus 0.225 x squared plus 3.62 x minus 11. I'm just showing all my work, and I want this to equal 0 if I'm going to find solutions. So I need to subtract 15 from both sides to get 0 again. So I do that, and I'm going to get s of x, or 0 equals, actually I shouldn't put s of x now, I should put 0 because s of x is 15. So now I have 0 equals 0.00547x to the third minus 0.225x squared plus 3.62x minus 26.0, if you will. Okay, so just to save time, I'm going to graph this, but before I do that, I'm going to look at Descartes' rule. And I have a change here, and a change here, and a change here. So it's 3 positive real solutions, or 3, I'm sorry, not 3, 1, because you subtract by even amounts, or there's 1 positive real solution. I'm not going to worry about negative solutions or imaginary solutions because it doesn't make sense in the context of the problem. When we're talking speed, speed cannot be negative. So we're only focusing on, we either have 3 or 1 real solution. So we're either going to cross the x-axis 3 times, which would be 1. So my x-axis could be like this. Okay, let me make that thinner. So my x-axis could be like that. So I have 1, 2, 3, or my x-axis could look like this. Make it thinner again, where I'm only crossing one place, like here, or maybe down here. Okay, so that's what we're trying to determine. Where is this thing crossing? Is it going to cross 3 times or once? So now I'm going to take that and put it in the calculator because of the crazy values. So if I go to my calculator and go to y equals and put 0.00547 x to the third, okay, minus 0.225 x squared plus 3.62 x minus 26, and hit enter and graph it. Okay, there it is over here. I don't care about negative, so I'm going to change my window for starters. I don't want any negative x's, so I'll put it at -1 just so we can see the axis, and hit graph again. So I'm not worried about what's going on over here because speed cannot be negative. And here's the function coming up, but we're not there yet when we use 10. So I'm going to change my window of x max to 20 and see what that looks like. Okay, so there's the function coming up, coming up, coming up, and I'm really not seeing enough yet, so I'm going to change that. I'm going to go out 10 more and make it 30. And then I'm just trying to show you, you just have to mess around with the window sometimes, and there it is. There goes that function. It is coming down, and if I want to see where it crosses the y-axis, then I can change my y minimum and go south further, so -20 instead, and hit graph. It's still not there, so I'm going to keep going. Window, go down here to -30. I'm extending my window. There it is right there. Coming up, crossing, turning, going back up. So there is only one real solution. It did not do this. It's crossing the x-axis. So it came up, it flattened out a little, it went up again. It's going to go up for infinity. So it is this scenario, not this one. So it's one real solution. Now I want to know what that solution is. The reason I did this in the calculator is now I can just go second calculate is blue, so I hit the second button and hit the trace button to get that calculator command. I want to know what the 0 is, so I go down to 0 and I hit enter. And now it says left bound, so I want to be left of the 0 and right of the 0, and it's going to find values in between. So there's my left. And to be right of the 0's here. I just need to go up a little because up is to the right. Hit enter, and then it says guess, and I hit enter, and I got x is approximately 19.863247. So I'm going to write that. So x is approximately 19.86. I'll just go out that far. Or x is approximately 19.9. And since x is the speed x in hundreds of RPM, so hundreds would be multiplying by 100, moves the decimal 2 places to the right. That would be 1990 or 1990 RPMs. And that's an approximation. Okay. And there you go. The tachometer is reading about 1990 RPMs. So that's how you do a real life application and using Descartes' rule to determine number of zeros. Now you should be able to do problem number 43. Okay, that brings us to the end of chapter 4.6. So here are the questions again that I asked you to do. And have fun, and thanks for watching.